Hey guys, we have our last part of section 2 in chapter 2 on polynomial functions. This time we're going to be emphasizing multiplicity. Multiplicity is a really easy concept. Multiplicity occurs anytime you have a repeated zero or a repeated factor. Multiplicity. So it's basically a count for any repeated factors or zeros. And in the classwork that we were doing today, you probably noticed that there were several of the polynomials that had repeated factors or zeros. And so I'm just going to give you a couple examples and show you how to describe the multiplicity. So if you had this polynomial, for example, say we had f of x is equal to x minus 1 squared times x plus 2 times x to the third. Okay, there are lots of factors and lots of zeros in this function. The first one you may notice is that we could rewrite this as x minus 1 times x minus 1. That's a repeated factor. It occurs twice in the function. Then we have our x plus 2. And then we have x cubed, which technically could be x times x times x. And so that's not only repeated, it's triplicated. There's actually 3 x's. So if we wanted to describe the multiplicity of this function, we would say that there's a 0 at 1, 0 with a multiplicity of 2. Because there's 2 places where you could plug in 1 and get a 0. With the negative 2, there is a 0 at negative 2, 0. But that has a single multiplicity, and so if we don't write multiplicity, it's assumed that it just occurs once. So you don't really need to write multiplicity next to that one. And then for our final portion here, we have 3 x's. So that means that if we plug in 0, we'll also have another 0 to this polynomial. But this would be multiplicity 3 now. Okay, and multiplicity might seem like it's kind of pointless because we're really just trying to solve the function for its x-intercepts, for its zeros. But multiplicity actually helps describe a lot about the graph. Anytime you have even multiplicity, this is important, so make sure you write this down in your notes. Anytime you have even multiplicity, the function touches the x-axis, but does not cross it. So make sure you write does not cross. Okay, so anytime there's even multiplicity at that x-intercept, it will still touch, it still has to be, that point has to exist there, but it's not going to actually cross the x-axis. It's going to touch it and then move back away to the same side of the x-axis it was on. If there are an odd counts of multiplicity, then it will actually cross through the x-axis like we're used to. And in our example today, when we sketch a graph of these, you'll see what I mean exactly by touching but not cross or crossing. Okay. Alright, so make sure you have those notes down. This is really important that you understand what happens at the different types of multiplicity. Okay, so for our final example in section 2, we're going to actually go ahead and sketch a graph of the polynomial function. This example has been given to you in factored form. We practiced factoring today. So if it's not given to you in factored form, you'd obviously want to factor it first. And we're going to apply the leading term test first. The leading term test will help us to sketch the graph. So my leading term test says I need to find my leading term, obviously. So let's see here. If I go ahead and distribute my first term, x times 2x, that would be 2x squared plus 3x. And then if I distribute that to, I'm going to go ahead and write x, this is really x minus 1 times x minus 1. You want to make sure you don't forget that that's being squared. Now I need to distribute the 2x squared times x, and then whatever I multiply with that, I want to distribute that to the other x as well. So we've got 2x squared times x times x. That means my leading term is going to be 2x to the fourth. Okay. So you want to make sure you correctly distribute, and you could have done it this way too. Some people just will simply say, okay, x minus 1 squared is x squared, times 2x is 2x cubed, times another x is 2x to the fourth, and that's fine too. But if you need to be careful and distribute a little bit so that you can see what your leading term will be, that's probably the safer way to do it. So my leading term is positive, and it's even. And because it's positive, I know the right side of my graph is going to go up, and because it's even, the left side is going to do the same thing that the right side is doing. So they go in the same direction. So we're going to apply the leading term test. It's going up and up. It doesn't actually say to solve for the end behavior, so we don't have to write the limit part down, but this will help us sketch the graph, so it's still good that we did it. We're next going to determine the zeros and state the multiplicity for any repeated zeros. So for part B, we're going to solve for all of our zeros. If we set our first one x equal to 0, that means we have the coordinate 0, 0. If we set 2x plus 3 equal to 0, it's my second factor right there, then I get that when I solve for x, I get that x is equal to negative 3 halves. That's going to be my second coordinate, negative 3 halves, 0. And then we have x minus 1, so when I set that equal to 0, I get that x equals 1. So we get the last one, 1, 0. Now, the first 2 points have no multiplicity. They only occur once in the function. We have x, that occurs once, 2x plus 3, that occurs once. But then x minus 1 is repeated. It's a repeated 0 there, so we have to describe this as multiplicity 2. Okay. The next part says to find a few additional points, and that's going to help us sketch the graph. I usually want to pick points that are easy to plug in and I can do mentally. So we want to see what we've got already. We already have a point at 0, 0, at negative 1.5, 0, and 1, 0. So maybe like another point that's more positive and another point that's more negative. So we'll do f of 2, plug that in. That's going to be 2 times 2 plus 3 times 2 minus 1 squared. And so it's not too bad. It's going to be 7 times 2 is 14. This is going to be 1 squared. So we get 14. Make sure you follow order of operations. So we have another coordinate at 2, 14. And we'll do one more. We'll do f of negative 2. So that would be 2 times negative 2 times, 2 times negative 2 plus 3, and then times negative 2 minus 1 squared. So this is 2 times, this is negative 4 plus 3, it's negative 1, times negative 3 squared. This is 9 times negative 2, it's going to be negative 18. So when we go to negative 2, we get negative 18. So there's just some other points, and we can see that the numbers are starting to get large. So if we plugged in 3 and 4, we know that at the ends it's going up to positive infinity. So it's probably not going to get too much easier for us there. Oops, wait a second. I just realized I made a mistake. There should be a negative 2 here. Let's make that change really quick. So we get positive 18, not negative 18. That makes more sense. Okay. So now for D, we're going to graph the function. So give yourself a good xy axis to graph off of. I'm going to put mine up here. We're going to plot the few points that we have that are easy to plot on the graph. My points here are pretty positive, so I'm going to adjust my graph so I have plenty of room up above. Okay. So we have the point 0, 0, goes through the origin. We have the point negative 1.50, so it goes through right here, halfway between negative 1 and negative 2, and then 1, 0. Okay. Now we know the graph is going to be going up and up on either end, so I can kind of just in my head now, just kind of do an imaginary sketching of this. It's going to have to do something like this, and then go through these points, and it's going to have to come up this way. Okay. So you should be imagining that in your head as you start to piece together what you're going to plug in. We can use our other 2 points that we had as well. So we have points at 2, 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 13, 14. There we go, 14. and we had a point at negative 2, 18. So it's going to be off the chart here. It's going to be negative 2, 15, 16, 17. It's going to be way up there. So we know that it's really up high at this point. Whoops. Okay, so I'm going to go ahead and start to connect these points. I see that my graph has to come down very drastically to get down in time to be at negative 1.5, 0. And then I can see, okay, my graph needs to come back up through the origin. Now, what happens here at 1, 0, since I have multiplicity 2, is that my graph is not going to cross through the x-axis at this point, but it's going to touch it and then turn right back around and go up. And that's why multiplicity is important. It helps us to sketch this graph. So notice where there were odd multiplicities, here at 0, 0, where it was a singular multiplicity, and here at the origin where it was a singular multiplicity. For those 2 points, it crosses through the x-axis, but at this point where the multiplicity is 2, it just touches it and then turns back around. So it never goes back down below the x-axis for this point. Okay, and that's good enough sketch for these problems. Okay. Alright, for your homework to finish off the video, I want you to try and draw a sketch of both of these functions. I will post the answers right at the end of the video. Okay, and that's it for today. Have a good one. Okay, you can see with these problems that all of them actually had odd multiplicities. This one third actually had a multiplicity of 3. So there's my point 1/3, 0. But it's still odd, so it's going to cross through the graph. And it crossed through, I kind of missed it, but it crosses through the origin at 0, 0, and it crosses through at 4, 0. And because of our M behavior, we know that it's decreasing. The leading term is negative 6x, or sorry, actually it's way more than that. It's negative 2x times x times 3x cubed. That would be 27. That's negative 54x to the 5th power. And because it's negative and odd, it's going to be going from positive on the left side, going down to negative infinity on the right. So that's how you get your M behavior. Okay. Very similar one for 6b. This one just required factoring, so you should have factored it to be negative x times x minus 4 times x plus 2. And so you got your zeros at negative 2, 0, and 4. And again, all of these had singular multiplicity. There were no repeated zeros in this one, so it just crosses through the graph simply. Okay, and again, your M behavior lets you know that on the left side it's going up and on the right side it's going down. That's it. Have a great one.